Introduction to data structure. A data structure is basically a group of data elements that are put together under one name, and which defines a particular way of sorting and organizing data in a computer so that it can be used efficiently. Definition: a data structure is a specialized format for organizing and sorting data. Data structure are used in almost every program or software system. Some common examples of data structures are arrays, linked list, queues, stacks, binary tree, and hash tables. Data structures are widely applied in the following areas. Application of data structure. 1. Compiler design. 2. Operating system. 3. Statistical analysis. 4. DBMS. 5. Numerical analysis. 6. Simulation. 7. Artificial intelligence. 8. Graphics. Need of data structure. Data structure is an important way of organizing information or data in a computer. It has different ways of sorting and organizing data in a computer. It helps to understand relationship of one data element to another. It helps to store data in logical manner. We need a way to store collection of data that may grow and shrink dynamically over time, and we need to organize the information so that we can access it using efficient algorithm. Abstract data type. Data type of a variable is a set of values that the variable can take. The basic data type in C are: include int, char, float, double. Abstract. The word abstract in the context of data structure means considered apart from the detailed specifications or implementations. An abstract data type, ADT, is the way we look at a data structure, focusing on what it does and ignoring how it does its job. An abstract data type is one where we can store elements and also perform certain operations on those elements. For example, stacks and queues are the perfect examples of ADT. We can implement both these ADTs using an array or a linked list. Advantages of using ADTs. In real world, programs evolve as a result of new requirements or constraints. So, a modification to a program commonly requires a change in one or more of its data structures. For e.g., if you want to add a new field to a student record to keep track of more information about each student, then it will be better to replace an array with linked structure to improve the programs efficiently. In such a scenario, rewriting every procedure that uses the changed structure is not desirable. Therefore, a better alternative is to separate the uses of a data structure from the details of its implementation. This is the principle underlying the uses of abstract data type. Classification of data structure/types. Data structure are generally categorized into two classes. 1. Primitive data structure. 2. Non-primitive data structure. 1. Primitive data structure. These are the fundamental data type, which are supported by a programming language. Some basic data types are integer, real, character, and Boolean. The item data type, basic data type, and primitive data type are often used interchangeably. 2. Non-primitive data structure are those data structure which are created using primitive data structures. Examples of such data structure include linked list, stacks, trees, and graphs. Non-primitive data structure can further be classified into two categories. A. Linear data structure. B. Nonlinear data structure. Linear and nonlinear data structure. If elements of data structure are stored in a linear or sequential order, then it is a linear data structure. E.g., include arrays, linked list, stacks, and queues. Linear data structure can be represented in memory in two different ways. One way is to have a linear relationship between elements by means of sequential memory locations. The other way is to have a linear relationship between elements by means of link. However, if the elements of a data structure are not stored in a sequential order, then it is nonlinear data structure includes trees and stacks. Classification of data structures. Linear data structure. 1. A data structure in which all data elements are stored in a sequence is known as linear data structure. 2. All elements are stored in contiguous memory location inside memory. 3. The data elements can be accessed in one time, single run. 4. Ineffective memory utilization. 5. E.g., stacks and queues. Nonlinear data structure. 1. A data structure in which all data elements are not stored in a sequence is known as nonlinear data structure. 2. All elements may store in non-contiguous memory locations inside memory. 3. Traveling of data elements in one go is not possible. 4. Effective memory utilization. 5. E.g., tree, graphs. Classification of data structure/types. Data structure 1. Primitive data type. 1. Integer. 2. Non-primitive data type 2. Real data. Types 3. Character. Array 4. String. Files 5. Pointer. List. 1. Linear 1. Stacks. 2. Nonlinear 2. Queue. 1. Tree. 2. Graph. Algorithms. Definition of formally defined procedure for performing some calculations is called algorithm. Different approach of designing an algorithm. 1. Top-down approach. A top-down design approach starts by dividing complex algorithm into one or more modules or subsystems. Each subsystem is then refined in yet greater detail, sometimes in many additional subsystem levels, until the entire specification is reduced to base elements. Top-down design method is a form-stepwise refinement, where we begin with the topmost module and incrementally add modules that have calls. 2. Bottom-up approach. In this approach, the individual base elements of the system are first specified in great detail. These elements are then linked together to form larger subsystems, which then in turn are clubbed in many levels, until a complete top level. Algorithm to add two numbers. Step 1. Input first number as A. Step 2. Input second number as B. Step 3. Set sum, A plus B. Step 4. Print sum. Step 5. End. Algorithm for swapping two values. Step 1. Input first number as A. Step 2. Input second number as B. Step 3. Set temp equals A. Step 4. Set A equals B. Step 5. Set B equals temp. Step 6. Print A, B. Step 7. END. Algorithm to find larger of two numbers. Step 1. Input first number as A. Step 2. Input second number as B. Step 3. If A greater than B. Print A. Else if A less than B. Print B. Else. Print the numbers are equal. End PF it. Step 4. END. Algorithm to find whether a number is even or odd. Step 1. Input number as A. Step 2. If A%2 is equal to 0. Print even. Else. Print odd. End of it. Step 3. END. Time complexity. Time complexity of a program/algorithm is the amount of computer time that it needs to run to completion. While calculating time complexity, we develop frequency count for all key statements, which are important and basic instructions of an algorithm. Example: consider three algorithms given below. Algorithm A equals A plus 1. Algorithm B, for x equals 1 to n step 1. A equals A plus 1. Loop. Algorithm C, for x equals 1 to n step 1. For Loop. Frequency count for algorithm A is 1 as A equals A plus 1 statement will execute only once. Frequency count for algorithm B is N as A equals A plus 1 is key statement executes N time as the loop runs time. Frequency count for algorithm C is N as A equals A plus 1 is key statement executes N squared time as the inner loop runs. N time, each time the outer loop runs, and the outer loop also runs for N times. Space complexity. Space complexity of a program/algorithm is the amount of memory that is needs to run to completion. The space needed by the program is the sum of the following components. Fixed space requirements. It includes space for instructions, for simple variables, fixed size structured variable, and constant. Variable space requirements. It consists of space needed by structure variable whose size depends on particular instance of variables. E.g. Additional space required when function uses recursion. Algorithm analysis. There are different ways of solving problems, and there are different algorithms which can be designed to solve a problem. There is a difference between problem and algorithm. A problem has single problem statement that describes it in general terms. Best case time complexity. It is the measure of minimum time that algorithm will require for input of size, and running time of many algorithms varies not only for inputs of different sizes, but also inputs of same sizes. For example, in running time of some sorting algorithms, sorting will depend on ordering of input data. Therefore, if input data of an item is presented in sorted order operation performed worst case time complexity. It is measure of maximum time that algorithm will require for input of size, and therefore, if various algorithm for sorting is taken into account, and say n input data items are supplied in reverse order for any sorting algorithm, then algorithm will require n squared operations to perform sort, which will correspond to worst case time complexity of algorithm. Average case time complexity. The time that an algorithm will require to execute typical input data of size n is known as average case time complexity. We can say that value that is obtained by running time of an algorithm for all possible inputs of size n can determine average case time complexity. Computation of exact time taken by algorithm for its execution is very difficult. Thus, work done by algorithm for execution of input of size n defines time. Operation on data structures. A. Insertion. It is adding a new data in data structure. B. Deletion. It is removing a data from existing data structure. C. Searching. It is finding location or existence of data within given data structures. D. Sorting. Arranging data in some logical order. It is used to arrange the data items in some order, i.e., in ascending or descending order in case of numerical data, and in case of alphanumerical data. E. Traversing. It is an operation that access each and every element. F. Merging. It is used to combine data items of two